All right. So this video is going to be the first of, I think, probably 3 videos is something I'm going to break it down to. For the first unit that's independent in the accelerated math class. So today we're going to be talking all about sequences, specifically arithmetic and geometric sequences, which you can see up on the board. Basically, the format for this whole independent thing is going to be there will be a few videos interspersed throughout whatever the content is that we're talking about. Some units it'll be every 3 or 4 assignments. Some units it'll be in between every single assignment. Specifically, that's like substitution and elimination because those are pretty complicated. But basically, I'm going to give you guys a whole bunch of information at one time, some stuff to practice, more information, more stuff to practice. The idea is that you work through it all the way through in some kind of relatively contained time frame, hopefully, maybe. This unit, I would say, probably is a 2-week thing. Would be my guess. You could probably do it faster if you really wanted to. Probably shouldn't take too much longer unless you're going really slow. My concern is just if you are going to start a unit and then come back to it like 2 weeks later, you'll probably forget a lot of what you learned at the start. So I would try to do these in some kind of relatively contained time frame. But anyway, hopefully the actual format of this will make more sense when you see everything that's in this unit. This video should be at the bottom if I placed everything correctly. Then there'll be a couple of assignments, which are assignments that I'm going to talk about in the video itself. And then we'll have another video and so on and so forth. And then once you get to the end, you'll be able to come talk to me and get the actual test for this unit for Algebra 1. But anyway, let's go ahead and just get into this. So we're talking about sequences here. And sequences are probably a term you aren't terribly familiar with in math. We don't talk about them very often, but they are kind of interesting and they're pretty important in specific aspects. So sequences are sets of numbers in some particular order. That's just the general term of them. They're pretty simple. There's nothing really horribly complicated about them, but this is a good example of a sequence. So we have 1, 2, 3, 4, 5, 6, 7. That's a sequence. It's just counting numbers, but it's going up by 1 every time. 2, 4, 6, 8, 10. That's just counting up the even numbers, or going up 2 every time. And then 1, 2, 3, or 1, 2, 4, 8, 16 is a sequence as well. And as you can tell, this is a different kind of sequence. We're not going up by the same amount each time. Instead, we're just multiplying by a number each time. There are also other different kinds of sequences. So for example, one sequence that you may be familiar with, let me change the pen to a color you'll be able to see, is something like this. So if I have 1, 1, 2, 3, 5, 8, 13, 21, so on and so forth. This is a different kind of sequence. This isn't a sequence that we'll actually talk about too much. But basically the whole point of the sequence is you add the 2 previous numbers together to get the next term. So we have 1 plus 1, that gives us 2. Then we have 2 plus 1, that gives us 3. And then we have 3 plus 2, that gives us 5. And then we have 5 plus 3, that gives us 8. And then 8 plus 5, 13. 13 plus 8, 21. And then you could add 21 to 13. You get the next number would be 34, and so on and so forth. So all of these are sequences. The ones we're going to focus on are mostly these, which we'll talk about in just a little bit. But it's worth knowing that there are other types of sequences that we don't talk about in this class. Perfect squares is another good example. So 1, 4, 9, 16. This is a sequence. And actually, if you write out the sequence, you might notice something kind of cool about perfect squares you didn't know before. This is a +3. So 0 would be the first one because 0 squared is 0. We had 1, we had 3, we had 5, we had 7, we add 9, and so on and so forth. And it'll actually work for all of the perfect squares. You can always just add the next odd number and you'll get the next perfect square. But that's not particularly relevant here. So we want to talk about what makes a sequence. So sequences have to have some kind of particular order, and they're composed of numbers that we call terms, just like we call them terms in algebraic expressions. So in this case, 1 is the first term in the sequence. We have 1, 5, 9, 13, and 17. 5 is the second term. 17 is the 5th term. So 1, 2, 3, 4, 5. Now, technically this sequence, because I have this ellipses at the end, this tells me that the sequence goes on forever, so I could keep adding 4. That being said, it starts here. This is the start of the sequence. It does not go lower. The ellipses is going in one direction specifically. You can have sequences like this, where it's just showing you part of the sequence. So like 1, 3, 5, 7. So this tells me that it continues on forever this way and on forever this way. So that is a thing you can do for sequences. We're almost exclusively looking at sequences that have a defined start, though. So that way we can use a first term. So there are two major types of sequences we're going to talk about: arithmetic sequences and geometric sequences. An arithmetic sequence is a sequence of numbers with a constant change. So the number is always going to be going up by the same amount, whether that's 2 or 4 or 6 or whatever, -3, 1/3. But as long as you're adding the same amount to each number to get the next one, or subtracting, I guess, whatever, however you want to think about it, but adding or subtracting to get to the next term, it's an arithmetic sequence. A geometric sequence is a sequence in which numbers change by multiplying the previous term. Now, sometimes it'll look like dividing, and you can think of it as multiplying or dividing if you want. Multiplying and dividing is the same as multiplying by a fraction, so whichever way you want to think about that is just fine. So we're going to focus in on arithmetic sequences for a little bit. This first video, a lot of it's background information, so I'm giving you a lot of stuff that's kind of going to be used throughout the unit, and then I'll get to specifically what's on each IXL assignment as we go. It is really important to pay attention to the part of the beginning, though, because you are going to have to take a test on this, and I'm not just going to expect you to be able to answer problems that were on the IXL. I expect you to actually know this stuff too. It's definitely worth taking notes on all of this. It's not technically required, but this is the kind of thing where if you guys are coming into a test really unprepared and then failing it, that's not going to look good. So an arithmetic sequence, or arithmetic sequences in general, are formed by adding or subtracting a certain amount between each term. They have the general formula t sub n equals t sub 1 plus n minus 1 times d. Now, this is a really complicated looking formula, so we want to break this down a little bit. T sub n is the nth term. So t just stands for term. The sub n means whatever number. So I could say that n is 5 if we're looking for the fifth term. So t sub 5 would be the fifth term in a sequence. And it tells me what n would be. So then I could replace n with 5. T sub 1 is the first term in the sequence. This is a really important part of these sequences. If you don't have a start to your sequence, then you just have this part right here. And that can get kind of confusing. So anyway, t sub n equals t sub 1 plus n minus 1 times d. N, this is just a number. We can pick whatever we want. It's the term number, basically. And then d is the common difference, or the rate of change. So what we mean here is, like, let's say a sequence is going up by 2. Right, so 2, 4, 6, 8, yada, yada, yada. Oh, whoops. Nice. 2, 4, 6, 8, so on and so forth. So t sub 1 would be 2. D, since this is going up by 2 every time, right? I'm adding 2 to get to the next number each time. D would be 2. And then I can pick whatever n I want, and this formula will let me solve for it. So let's say I wanted to figure out the 15th term. I'd sub in 15 for n, so I'd say t sub 15 equals term 1, which is 2, plus n minus 1, so 15 minus 1 times 2. 15 minus 1 is 14, times 2 is 28, plus 2 is 30. So 15th term in this sequence would be 30, which makes sense, right? We're just going up by even numbers. So the first term is 2, the second term is 4, the third term is 6. It's just double whatever your actual number of the term is. And then the other important thing to note here is that arithmetic sequences are linear in nature. This is something that'll make a lot of difference when we look at the graphs of these, which we'll do in just a little bit. But linear equations are really what Algebra 1 is all about. So arithmetic sequences are a really big focus. So here's some examples of arithmetic sequences. We have 1, 3, 5, 7, 9, 11. These are just all the odd numbers. T sub 1 is 1. That's that first term in the sequence. D is 2 because it goes up by 2 every time. We add 2 to get to the next number. Here we have 6, 10, 14, 18, 22. Our first term, T1, is 6. And the difference to get from 6 to 10, we have to add 4. To get from 10 to 14, we add 4. So our D is going to be 4 once again. Here we have 23, 13, 3, -7, -17. So this one, T sub 1 is 23. Again, that's pretty easy to find. And then D is equal to -10. The reason is we're adding a -10, basically. Your D should always be, when you're calculating D, you should always think of it as what are you adding. So in this case, we're adding a -10. We're subtracting 10. It's the same idea. But basically, you put that negative symbol into the actual d. And on the actual test, you will need to be able to solve for these, but it'll show up in a little bit of a different way, and we'll look at that later. So here's some graphs of arithmetic sequences. We said they're linear in nature. Basically what that means, and we'll talk about this more in class when we get to our graphing lines unit, but in general, linear things make a straight line when you graph them. So graphs of arithmetic sequences will always form straight lines, and these can be horizontal or diagonal, although I will say you're usually not going to see horizontal ones, just because that sequence would be, there would be no change in that sequence. It's just going up by 0 every time. Doesn't make a whole lot of sense. So this is a graph of a linear sequence right here. This is also a graph of a linear sequence. And this is technically a graph of linear sequence, but it's a little bit of a weird linear sequence. This is also technically a geometric sequence, so that can get a little bit confusing. Now, where you see arithmetic sequences in the real world, and this is actually really important because there's really no point in talking about these if we can't think of ways that they would apply to our real life. So basically anything in the real world with a constant rate of change. A car that's driving at a constant speed. So if a car is moving at 20 miles an hour consistently, then its distance is changing at a rate of 20 each time. So the first hour it goes 20 miles, the second hour it goes 40 miles, the third hour it goes 60 miles, the fourth hour it goes 80 miles, and so on and so forth. So you'd have an arithmetic sequence of adding 20. Water flowing through a faucet, because the amount of water coming out at any given time is going to be constant. Ironically, the height of it in somewhere, depending on the shape of the thing, can actually be either geometric or arithmetic, but we won't worry about that. If you think about water flowing in general, it's going to be an arithmetic sequence because the amount coming over is the same. So like Niagara Falls, if I remember right, it's something like 6 million gallons per minute or something like that of water that goes over the falls, something ridiculous. But so for the first minute, you'd have 6 million, second minute, you have 12, and so on and so forth. And so that would just go up by 6 million every time, or whatever the number is. And then the number of chairs in a stadium as you add more rows. So if we think of like bleachers, right, let's say the first row can fit 10 seats, 1, 2, whatever. This is not going to be 10, but it doesn't really matter. And then you add a second row, you have twice as many. So let's say this hold 10, now you hold 20, then you hold 30, then you hold 40, then you hold 50, and so on and so forth. So again, we have an arithmetic sequence because it's going up by 10 every time. So these are just some examples. There are plenty of other ones that you can think of, but these are some of the more common ones, or at least the easiest to visualize, that are also very different from each other. Now let's talk about geometric sequences. So these ones are much more complicated. They're things that we're going to run into that are a little bit trickier to work with. And we won't use these as much in our class. This is more of an Algebra 2 thing. You work with a lot of geometric sequences, but you guys need to know how to solve them, at least at this point. We won't play around with the graphs of them too much in either our class or in the accelerated math class, but it is worth knowing what they look like and how they work. So a geometric sequence is formed when you multiply each term in a sequence by a common factor. So it's always being multiplied by some number. The general formula for a geometric sequence is T sub n equals T sub 1 times r to the n minus 1. So again, whole bunch of different things. This looks more complicated than it actually is, but let's break it down and think about it. So T sub n is, again, just the nth term in the sequence. So n, I could pick whatever term I want. I could solve for the 30th term in a sequence if I wanted to, and I just put in 30 for n. So that's just whatever term I want to look at. T sub 1 is, again, the first term in the geometric sequence. It's an important one. And then r is the multiplying factor. So like, let's say I had the sequence 2, 4, 8, 16, and then it'd be 32 and so on and so forth. But basically just doubling every time. I'm multiplying by 2, multiplied by 2, multiplied by 2. Okay, so that forms a geometric sequence. My r value in this case would be 2. My T sub n would be 2. Or sorry, my T sub 1 would be 2, not my T sub n. So I'd have 2 times 2 the n minus 1 equals T sub n. And this is what the actual formulas will look like. And then you can just plug in whatever number you want for n. So if I want to find, let's say, the 6th factor, or the 6th term in the sequence, what I could do is T sub 6 equals 2 times 2 to the 6 minus 1 is 5. 2 times 2 to the 5th, which is the same as 2 to the 6th in this specific case. And 2 to the 6th is going to be 64, I believe. 2 squared is 4 times 4 times 4. Yeah, 64. So this would be 64 would be our 6th term. And here we have the 4th term, so 5th would be 32, and then we double that to get 64. Now, you might be thinking, well, hold on, I could just write these out. Why would I bother with this? The reason you want to use the formula is like, let's say I want to find n equals 72. You're not going to want to write out 72 terms in these sequences. So just being able to plug it into this formula, to be fair, you wouldn't want to solve this for 72 either, but it'd be a lot easier than trying to figure out trying to write it all out by hand, basically. So here's a few examples of geometric sequences. Here we have 3, 6, 12, 24, 48, 5, 15, 45, 135. So this one, we're doubling each time. So our R is going to be 2, and our first term is 3. So again, the T sub 1 is super easy, right? You just look for whatever term is first. That's not hard to figure out. And then the R value, you can just look from one number to the next to figure out what it's actually going to be. So to get from 5 to 15, we have to multiply by 3. So assuming this is actually geometric sequence, which we can check, it's always going to be times 3. And 15 times 3 does give us 45. 45 times 3 does give us 135. This one might look a little bit weird. Our first term is obviously 50 here, but then we got to figure out, what do we multiply 50 by to get 10? The answer in this case is 1/5. So basically you're dividing by 5, or you're multiplying by 1/5. Those are the same thing. So we multiply by 1/5, we multiply by 1/5, we multiply by 1/5. And that should continue all the way down. Now, this one I wanted to bring up just as kind of an interesting side note. So our first term is obviously 1. And then you'll notice this goes to -2. So we multiplied by -2. That's the only thing you can do to get from 1 to a different number. You multiply by whatever the number is. So we have -2. And interestingly, when you have an R term, or when your multiplier is negative, every other term is going to be negative, and every other term is going to be positive. So we have a positive, negative, positive, negative, positive. If you ever see a pattern like this, where it's positive, negative, positive, negative, positive, negative, so on and so forth, it's always going to be a geometric sequence, and your R value is always going to be a negative term. So that's just something to keep in mind. Here's what the graphs of geometric sequences look like. I didn't mention on the last page, the other part that was on there, or 2 pages ago, sorry, where it said that geometric sequences, when graphed, are exponential in nature. What this means is basically that it gives you a curve. So either a curve like this or a curve like this. Either one is going to be geometric. This is a geometric, the one on the right is a geometric with a fraction, so you're multiplying by something that makes it smaller. The one on the right is multiplying by a whole number, which makes it bigger. Now, real-world geometric sequences show up as things with exponential changes, which is kind of a weird word to think about. We talked about a few of them in our actual exponents unit in class, but you'll also talk about a lot of these if you take physical science next year. So bacterial growth is one. A bouncing ball is negative. So when a ball bounces, it comes down, it bounces pretty high, and then it bounces less high, and then it bounces high and lower. And although there's some loss to friction in things, generally speaking, this forms an exponential curve if you graph the heights. So like maybe the first time it bounces 10, and then 5, and then 2.5, and then 1.25, and so on and so forth. It should reduce by about the same amount each time. And obviously, as you go further in all these real world things, they reach a limit. So same with the bacterial growth. It'll start like this. It'll start really low. You won't see a whole lot, and then it'll start to explode as you get more and more. But eventually you do hit a capacity and it'll level back out. So the geometric part is from here to here. So the first IXL we're going to look at is identifying sequences as either arithmetic or geometric. It's relatively simple. We're basically just looking at the change, a constant number that we can add, or is it something being multiplied each time? So we want to be able to identify them as arithmetic, geometric, both, or neither. And because I'm not good at developing slideshows, I actually gave you one of these for, this should have an extra one at the beginning, by the way. I gave you one of each, and there in order. But anyway, if we look at this one, we have 3, then 15, then 27, then 39, and then 51. So hopefully you notice that if we multiply by 5, that would become 15. If we multiply this by 5, we definitely don't get 27. So we can immediately rule out geometric. That's not going to work. We have to add 12 to go from 3 to 15. If we add 12 again, we do go from 15 to 27. We add 12 again, we do go from 27 to 39. And again, we add 12, we will get to 51. So this, since we're adding 12 every time, is an arithmetic sequence. So that's number 1 done. The next one I gave you, or I talked about this right at the end of geometric sequences. If we ever see positive, negative, we know it's going to be geometric, but also we can say, okay, this is times -2, times -2, times -2. So we're multiplying by -2 each time here. So this is in fact geometric. The next one, we go from 8 to 8 to 8 to 8 to 8. So this is actually, if we were to graph this is what I was talking about when I was talking about horizontal lines. This would just form a horizontal line where you have an 8, because it's always staying the same. So in order to get this, obviously we add 0, we add 0, we add 0, we add 0. Now you might be thinking, okay, well then clearly it's arithmetic, but I can also multiply by 1 each time, and this is still going to give me 8 every single time. So this is actually both. Now, interestingly, if I did this instead, 8, -8, 8, -8, 8, this becomes just geometric. The only way I can do this is by multiplying by -1. In order to go from here to here, I had to subtract 16, and then I had to add 16, and that's not an arithmetic sequence. The change is not constant; it's going back and forth. So if some of these were negative, this would actually be a geometric sequence. But in this case, since it's all just positive 8s, it's going to be both. And then the last one, as I'm sure you can guess from process of elimination, is actually the sequence I showed near the start. So the 1, 1, 2, 3, where we just add the previous 2 terms in order to get the next one. And this would be neither. This is a different kind of sequence. These kinds of sequences usually have their own unique names. There's a few different ways you can do them, and they could be there's some pretty interesting ones, but none that we really need to worry about right now. I'm sure that Mr. Rice will teach you all about them when you get to geometry class, though. So the second IXL that we're going to work on, and this is yeah, okay. So this is the other 2 IXLs that we're going to be working on for this video specifically. These are IXL P2 and P3. A couple of you have already started these because these are things that you can kind of do without actually having been taught this before. It's just looking for patterns in numbers. But basically what you want to do is figure out, okay, what's the amount that's changing by and where are the gaps? So here I have 2, 5, blank, 11, 14, 17. So in order to get from here to here, it could potentially be times 2.5, but chances are if you see something like that, it's going to not be multiplication. So if we add 3, we go from 2 to 5. If we add 3, we do go from 11 to 14. And then adding 3 does take us from 14 to 17. So we know we're adding 3 every time. So all we need to do is figure out what we do when we add 3, and that's going to give us an 8. So it shouldn't be too terribly difficult to fill in the sequence here. For the next one, we have 3, blank, 12, 24, and 48. So the difference between these 2 is 12. The difference between these 2 is 24. So that's getting bigger as we go. So we know it's not an arithmetic sequence. If we look for a geometric, we double this. That brings us from 12 to 24. We double this to get from 24 to 20 or 48. So we probably know we're going to have to double this. 3 times 2 gives us 6. 6 times 2 does in fact give us 12, so we know that this works. So 6 is our missing number. The last one is a little bit trickier. We only have 3 terms in the middle, and we don't have the start or the end, which can be a little bit confusing. But you just need to look for what we're actually changing it by each time. So in this case, to get from -6 to -10, those of you who need practice with negatives, this one might be a little tricky to figure out. But what we're adding here is -4. So it's getting more negative by 4 each time. Again, add -4. So here we can add -4. -14 plus -4, that's -18. And then to go the other way, we have to actually subtract backwards. So In this case, since we're going 4 smaller, 4 smaller, 4 smaller, here we have to go 4 bigger. So this gives us -2. And I believe, let me double check. Yeah, that's all we need for the first few sets of IXLs. So after watching this video, you should be able to complete IXL P1, P2, and P3. Now, during this accelerated math program, I am actually making you go to a minimum of 90. The reason is because I want you to really learn this content. It's not just because I want you to do a whole bunch of problems. I want you to be able to get this down. So you can go further than that. That's totally fine if you want to go all the way to 100. It will just be extra preparation for you for your test, so it's not a bad thing. That being said, I know it takes a lot of time once you get even past 80, but once you get past 90, I know it goes really slow. So if you don't want to go all the way to 100, that's fine. One thing I will suggest is please take your time on these. I saw a couple people today actually that were rushing a little bit to try to get through them. You end up making a lot more mistakes that way, and it takes you a lot longer. So just take your time, go slow, make sure you're getting the right answer on each of these. For right now, all I have in this unit is IXLs because that's all that the high school uses. I will consider, depending on how this first unit kind of goes, adding in more assignments that I think are useful, but I don't know whether I'm going to require those or what just yet. So for now, we're going to play it by ear and see how things go. So these will be the first 3 that go along with this video. Please get these done before you watch the second video so you don't get too confused. But yeah, that should be about it for this one. So